Welcome to the deep dive. Today, we're tackling something pretty fundamental. We're going to try and boil down the core ideas of the very first chapter of the Feynman lectures on physics.
Volume 1, Chapter 1, Atoms in Motion.
Right. And it's not just, an intro to physics equations. It's really a lesson in how physicists think. Feynman kicks off his course, not with formulas, but with this kind of philosophical point. He tells you, the student, right away, that all scientific knowledge, it's approximate.
Yeah.
We're dealing with, best guesses that lead constant tweaking. Knowledge is always provisional, driven by experiments and needing correction.
And what's really sharp about that opening is the dilemma he points out for anyone teaching this stuff.
Okay.
Do you teach the simpler approximate laws, like, say, assuming mass is always constant? Or do you dive right into the correct but much harder laws, like relativity, where mass actually changes with speed?
That seems like a small difference, maybe.
Well, you'd think. If the law is off by just 1 part in a million, why make it so complicated? But Feynman's point is profound. Even that tiny difference, the fact that mass does change slightly, forces a huge philosophical shift. You can't just patch the old theory. You kind of have to throw out the whole picture and rebuild. That insistence on the right philosophy, even for tiny effects, that's real physics, according to him.
That's a fascinating start. Takes imagination just to even frame the problem correctly. So, okay, let's shift from the philosophy to maybe the most powerful bit of knowledge we have.
Right.
Feynman poses this thought experiment. If some catastrophe wiped out almost all scientific knowledge and you had one sentence to pass on, what would it be?
And his answer is the atomic hypothesis.
Exactly.
And that sentence, the most powerful one, it's this. All things are made of atoms, little particles that move around in perpetual motion, attracting each other when they're a little distance apart, but repelling when you squeeze them together.
Wow.
Think about it. Just that one sentence, plus some serious thought and imagination. You can pretty much figure out everything else we're going to talk about.
Okay, but to really feel that, we need to grasp the scale, right? Let's take a tiny drop of water, like a 1/4-inch cube.
Okay.
If we magnify that drop until it's, 15 miles across like a giant stadium, the individual molecules, they'd still just be like tiny specks of dust jostling around.
It's almost impossible to visualize.
So maybe the classic analogy helps. If you take an apple and blow it up to the size of the entire Earth, how big are the atoms inside that giant Earth apple?
They'd be the size of the original apple.
That's incredible.
Yeah, that's the scale we're talking about. Atoms are typically just 1 or 2 angstroms across. That's 10 air centimeters. It really puts things in perspective.
Okay, so they're tiny little particles. And knowing they're always moving and have these push-pull forces, that's enough to explain states of matter. Let's start with liquid water.
Right. In a liquid, the atoms, or molecules in water's case, are jiggling. They're moving fast enough to slide past each other. That's why it flows.
That they stick together.
Yeah, the attraction is still strong enough to keep them clumped together, so the volume stays pretty much the same.
Okay, now add heat. Increase that jiggling.
Eventually, the motion gets so wild it overcomes the attraction completely. That's steam, a gas. The molecules just fly off in all directions, filling whatever container they're in.
And the density plummets, right. Most of it is empty space.
Exactly. If you could see it, it'd look mostly empty with these molecules whizzing around. And that constant whizzing, that perpetual motion, that's what causes gas pressure.
How so?
Well, imagine a cylinder with a piston. The gas molecules are constantly banging against the walls, against the piston face. Billions and billions of tiny impacts. That collective force is pressure.
And it depends on how many molecules there are and how fast they're moving.
Precisely. Pressure is proportional to how many molecules in a given space.
Yeah.
And their speed, which is basically what we feel as temperature.
Okay, this leads to something really neat. You said heat is motion. What if we push that piston in, compressing the gas slowly? We're not adding heat from outside, but the gas gets hotter. Why?
Right. This is clever. Think about an atom hitting that piston. If the piston is moving inward, when the atom hits it, it's like hitting a moving wall. The atom bounces off faster than it came in. It picks up extra speed, extra kinetic energy from the moving piston.
And since all the atoms eventually hit that wall,
the whole gas gains kinetic energy. The average speed goes up, and that means the temperature increases. It's pure mechanics work done on the gas becomes heat.
Turning work into heat? Cool. Okay, let's go the other way. Decrease the temperature, slow down the jiggling.
If the water molecules slow down enough, those attractive forces take over completely. They lock the molecules into a fixed ordered pattern. That's a crystal. Ice.
A crystalline array.
Yep. But even in a solid, The atoms aren't still, they're just vibrating vigorously in place. That vibration is the heat in the solid.
And the structure of ice is kind of special, isn't it? It has that six-fold symmetry we see in snowflakes.
Exactly, that hexagonal pattern. But the really surprising thing structurally is that ice has these big gaps, these holes, in its crystal lattice. It's a very open structure.
Which explains.
Why water shrinks when it melts. When the ice melts, that rigid open structure collapses a bit. The molecules can actually pack slightly closer together in the liquid phase. It's unusual. Most things expand when they melt.
Interesting. And you mentioned heat is vibration. Does it ever stop?
Almost. At absolute zero, theory says all random motion should cease, but quantum mechanics throws a wrench in that. There's always a minimum residual vibration called zero-point energy, except maybe for helium, which is weird. It doesn't freeze at atmospheric pressure, even at absolute zero. Needs pressure.
Okay, let's move from the bulk structure to what happens at the boundary, like the surface of water evaporating. What's the atomic picture there?
Well, it looks calm, but it's actually incredibly busy. There's a dynamic equilibrium. Molecules in the liquid are constantly jiggling. Every so often, one near the surface gets enough energy, a big enough kick, to break free from its neighbor's attraction and fly off into the air.
Escaping.
Right. But at the same time, water molecules already in the air, water vapor, are constantly flying back down and getting snagged by the liquid surface again, leaving and returning all the time.
So if that's happening, why does evaporation make things cold? Like when I blow on hot soup.
That's the key. Think about which molecules manage to escape. It's only the ones with higher than average energy, the really fast ones, that can overcome the pull of the other molecules.
Okay.
So if you're constantly removing the fastest, most energetic molecules from the soup, what happens to the average energy of the ones left behind?
It goes down.
Exactly. Lower average kinetic energy means lower temperature. The liquid cools down because it's losing its most energetic members. Blowing just speeds up the removal of those escapees from the air above so more can leave.
And the reverse must be true, too. When vapor condenses back into liquid.
Absolutely. When a vapor molecule comes near the surface, the liquid molecules pull it in quite strongly. That pull accelerates it just before it hits, adding energy to the liquid. So condensation actually heats the surface.
This attraction-repulsion thing is everywhere. What about dissolving salt in water?
Same principle, basically. Salt isn't molecules like water. It's a crystal made of charged ions, positive sodium, Nau, and negative chloride, Auto. Water molecules, HO, are polar. The oxygen end is slightly negative, and the hydrogen ends are slightly positive. So the water molecules cluster around the ions in the salt crystal. The negative oxygens pull on the positive sodiums, and the positive hydrogens pull on the negative chlorides.
And they just pull them loose.
Yep, they wiggle them free from the crystal structure, surrounding them and carrying them off into the water. That's dissolution. It keeps happening until an equilibrium is reached, where ions are leaving the crystal and reattaching at the same rate. It also shows the idea of a molecule is a bit fuzzy for something like salt compared to water.
Okay, so evaporation, dissolution, these are physical processes. The atoms keep their partners, but chemistry, that's where the partners change, right?
Exactly. Chemical reactions are all about the rearrangement of atomic partnerships.
Got an example.
A really vivid one is burning carbon, like coal or charcoal in oxygen. Oxygen in the air exists as O-Rho molecules, two oxygen atoms paired up. Carbon atoms are long in a solid lattice.
Okay.
When you get them hot enough, the O-Rho molecules break apart. The individual oxygen atoms then find carbon atoms, and they grab onto them much more strongly than they were attached to each other, or the carbon atoms were to each other. They form CO, carbon monoxide, or CoO, carbon dioxide.
And that releases energy?
A huge amount of energy. That strong attraction means they snap together violently, releasing lots of kinetic energy. That's the heat and light of the flame. The new arrangement, CO or CO arrow, is much more stable, lower energy.
That complexity ramps up incredibly fast with bigger molecules, especially in organic chemistry. Feynman uses the example of the smell of violets.
Oh yeah. That distinct smell comes from a single type of molecule, but it's a beast. A complex arrangement of carbon, hydrogen, and oxygen atoms all locked together in a very specific three-dimensional shape.
And the name is something ridiculous like 4,2,2,3,6 tetramethyl something something 3-butan-2,1.
Yeah, exactly. But that crazy long name isn't just for show. It has to describe precisely where every single atom is connected to every other atom in that 3D structure. Because the function in this case, how it fits into receptors in your nose to trigger the violet signal, depends entirely on that exact shape.
And figuring out those shapes, that was serious detective work for chemists, right?
Right.
before modern tools.
Absolutely decades of painstaking work, mixing things, reacting them, analyzing the products, and inferring the structure piece by piece, like solving an incredibly complex jigsaw puzzle blindfolded.
And the amazing part.
The amazing part is that modern physical methods, especially X-ray diffraction, which lets us essentially see where the atoms are in a crystal, these methods have overwhelmingly confirmed the structures that chemists deduced purely through chemical reasoning. It's a beautiful validation of the whole atomic picture.
Okay, so we've built this whole picture based on the atomic hypothesis. But what's the solid proof? The observable evidence that these perpetually moving atoms are actually real. Feynman highlights two key things. First, Brownian motion.
Right. This was historically crucial. If you look through a microscope at tiny but visible particles like pollen grains or dust suspended in water or air, you see them jiggling around randomly perpetually because they're constantly being bombarded by the much smaller, invisible atoms of the fluid they're in. The bombardment isn't perfectly even at any given instant. Sometimes more atoms hit one side than the other. That tiny imbalance pushes the visible particle around. It's like a giant beach ball being jostled by a crowd of invisible people. It proves the atoms are real and they never stop moving.
Okay, undeniable motion. What's the second proof? It relates to the solids, the crystals.
Yes, the very existence and nature of crystal structure. When you look at well-formed crystals, salt, quartz, snowflakes, the angles between their flat faces are always precise and consistent for that substance.
And that geometry.
That perfect external geometry is a direct reflection of the underlying orderly arrangement of the atoms inside. And again, methods like X-ray analysis confirm this beautifully. They show the atoms lined up in repeating layers and patterns, exactly as needed to produce those crystal shapes. It confirms solids are just structured piles of atoms.
So pulling this all together, what's the biggest takeaway, maybe especially for someone interested in life sciences, in biology?
It's perhaps the most profound implication Feynman mentions in the chapter. The single most important hypothesis in all of biology is that everything living things do can be understood from the viewpoint that they are made of atoms acting according to the laws of physics.
Wow, that's a powerful statement.
It's the ultimate reductionist idea. Life isn't some magical force separate from physics. It's what happens when atoms, following physical laws, get organized in incredibly complex ways.
So let's think about that. If relatively simple arrangements of atoms repeating patterns like in steel or dynamic but uniform stuff like water can lead to phenomena like freezing, boiling, pressure, crystal shapes, then what happens when you have arrangements of atoms that are not simple, not repeating? Arrangements that are constantly changing and incredibly intricate like, well, like us, a human being.
The possibilities become practically infinite. The sheer complexity that can arise from arranging these simple building blocks in non-repeating dynamic ways. It allows for, well, everything we see in life. Structure, function, behavior. Marvels.
Okay, so we've kind of journeyed through the layers today. Started with the philosophy science as approximation.
Right, the intellectual honesty of it.
Then the core idea, the atomic hypothesis, explaining states of matter through motion and forces.
Liquids, gases, solids. All just atoms jiggling and sticking.
We saw dynamics like evaporation causing cooling purely through energy transfer.
And chemical reactions as atoms swapping partners for more stable arrangements.
And finally, the evidence Brownian motion and crystal structures proving it's all real.
Yep, a pretty complete picture just from that one starting sentence.
So maybe a final thought to leave everyone with, building on that biological connection.
Consider this. The atoms making up your body obey the exact same simple physical laws as the atoms in a rock or a glass of water. There's nothing special about your atoms, yet their specific, incredibly complex, non-repeating arrangement allows for consciousness, for learning, for you listening to this right now.
That jump from simple laws to complex phenomena.
How does that happen? How does organization breathe fire into the equation, so to speak? Thinking about that leap from vibrating atoms to, say, a thought, that's maybe the deepest mystery and the greatest testament to the power of organization within nature's rules.